Hi folks! The following video is our third one on alkanes. I'm going to be talking about cyclic alkanes, also known as cycloalkanes. When we're thinking about cycloalkanes, we're going to think about how the size of the ring relates to its stability and whether or not there is strain in the molecule, making it less stable. One type of strain that might be present in cycloalkanes is angle strain. This is when your atom that's a part of the ring, that is sp3 hybridized, has bond angles that are not 109.5 degrees. Because tetrahedral carbons prefer to form bonds with 109.5 degree angles between them, the molecule is strained if you deviate from this ideal bond angle. Another type of strain that can be present in cyclic alkanes is known as torsional strain. This is strain due to eclipsing interactions, like the type that we saw in Newman projections for eclipsed conformations. Our smallest ring that we can have is cyclopropane. This is a ring with 3 carbons in it. Cyclopropane has severe angle strain. To be in a 3-membered ring, this bond angle for each carbon is 60 degrees compared to the preferred 109.5 degrees. So a huge difference between the actual and preferred bond angle. Cyclopropane also has significant torsional strain. You can imagine looking down one of the carbon-carbon bonds of cyclopropane and then drawing a Newman projection. Here is a view down one of the bonds of cyclopropane. I have a front carbon and a back carbon, and connected to both of these is a separate carbon that's drawn as a CH2 group here. Notice that the hydrogens on the front and the back carbons are eclipsing each other. This is unfavorable, and it's one of the reasons that cyclopropane is so strained, in addition to the angle strain. The 4-carbon cyclic alkane is cyclobutane. This still has some angle strain, but less than cyclopropane has. Cyclobutane also has some torsional strain, but again less than cyclopropane does. To avoid having a lot of eclipsing interactions, cyclobutane is not flat. Instead, it adopts this puckered shape. In this puckered conformation, there's a bond angle of 88 degrees. Our 5-carbon ring is known as cyclopentane. As you get more carbons in the ring, there is less angle or torsional strain present. Rather than being flat, the cyclopentane molecule adopts an also sort of puckered shape, where this carbon is higher than the ones it's connected to. Adopting this puckered conformation removes some of the eclipsing interactions for cyclopentane. And our 6-carbon ring, which you're going to draw a lot during organic chemistry, is cyclohexane. And it turns out that cyclohexane is able to adopt a conformation where it is nearly strain-free. The angles are just about 109.5 degrees, and in the conformation I'll show you later in the video, there aren't any eclipsing interactions either. Within cyclohexane, several conformations are possible. You get to these by rotating around the positions of the carbons in the molecule. The conformation we'll deal with mostly is known as the chair conformation. Here is an example of a chair conformation for cyclohexane. The chair conformation will always have the general form of this kind of zigzaggy structure, but there are always 2 different chair conformations for a cyclohexane. Cyclohexane can undergo what's known as a ring flip, and this converts the cyclohexane into the other chair conformation. Notice that in one of these structures, like my highest point carbon is on the right, and in the other structure, my highest point carbon is on the left. During and after today's video, I recommend taking a lot of time to practice drawing these chair conformations. It will take a lot of practice. There are 5 steps that I use in order to draw a chair conformation. The first one of these is to draw a wide V. Then you're going to pick one of the carbons on the end of your V and draw a 60-degree line toward the middle of the V. Then, from the end point that you just stopped at, you're going to want to draw a line parallel to the other side of your original V. On the other side of your V, you'll want to draw a line parallel to the one you drew in step 2, in this case the orange one. And then you'll end by connecting the lines from your steps 3 and 4. So these 5 steps got me one of my 2 chair conformations. I'm going to repeat the process, but now drawing my number 2 step on the left side instead to get my other chair conformation. And here's that final chair conformation, angled the other way around. The ring flip that I mentioned previously converts between my 2 different conformations of a cyclohexane ring. And these 2 conformations are different from each other. For example, if you had an X group attached to one of the carbons, in one conformation it would point straight up, and in the other conformation, it's pointing up and out to the side. I want to show you a potential energy diagram for this ring flip event. I'm going to start out with one of my 2 chair conformations. The first step of the ring flip is to convert from a chair to a half chair. You get here by having this lower carbon come up. I think of the half chair as having sort of a lounge chair shape to it, in that this part is flat, and then one carbon is pointing up. The molecule starts to twist itself and goes to a lower energy structure known as a twist boat. As the carbon on the left continues to get twisted upward on the page, the next conformation is known as a boat conformation. In this, you have 2 parallel lines of carbons, and then 2 carbons higher than the others. You start to bring your high right carbon down and get to another twist boat structure. This goes back higher in energy to make a different half chair structure. Notice that my lounge chair is now angled the opposite direction and looks like a mirror image of my other half chair. Then as I bring this far right carbon down, I get to my final other chair structure. Here are the different energies for the different conformations shown on this chart. The 2 different chair conformations are equal in energy and are the lowest energy ones on the diagram. In addition to the positions of the carbons in the cyclohexane chair conformation, we also have to think about where the different substituents will go. These could be hydrogens or other atoms attached to the cyclohexane ring. We'll call axial substituents the ones that point straight up and down off of the cyclohexane ring. Notice that in my cyclohexane ring, I have 3 carbons that look like peaks. On the upper left, middle bottom, and upper right. From these carbons that are peaks, the axial substituents will point straight up. Here are those axial substituents pointing straight up. My other carbons, which look like V's rather than peaks, will have axial substituents pointing straight down instead. Notice that as you go around the cyclohexane ring, you alternate between carbons where you have axial up and then axial down. Each carbon also has an equatorial substituent, and these are going to point out of the ring rather than up or down from it, and they're going to alternate pointing angled up or angled down. To place these, we're going to want to imagine the right and left sides of our cyclohexane chair conformation. On the right side, all of the equatorial substituents will point toward the right. Let's start with this top right carbon. Because it already has an axial substituent pointed up, its equatorial substituent will point down. Because it's equatorial, though, it will point out rather than straight down. My lower right carbon has an axial down substituent, and its equatorial substituent will point up and to the right. And then my last carbon to the right side of the molecule, it has axial up, so it's going to have equatorial down. Notice that all the blue lines I drew are pointed vaguely toward the right side of the page. For the left half of my molecule, my equatorial substituents are going to point toward the left side instead. I'll have one pointed up and to the left, down and to the left, and up and to the left. Looking at this diagram, I want you to notice that each carbon has one axial and one equatorial substituent on it. Now let's consider what this ring flip would look like if we have a substituent on the cyclohexane ring that isn't a hydrogen. For example, replacing one hydrogen with a fluorine to have fluorocyclohexane. In one of my 2 chair conformations, this fluorine is going to be axial. It's going to point straight up or straight down from the ring. In this example, I've drawn it on the upper right carbon, where the axial position points straight up on the page. This conformation is the same as these other 2 that I've drawn. Notice that in all of these conformations, the fluorine is axial, pointed either straight up or straight down from the ring. You could rotate these molecules to make them look like the original axial one I drew. This chair conformation of fluorocyclohexane is in equilibrium with another chair conformation. In the other chair conformation, the fluorine is equatorial instead of axial. These 2 conformations, where fluorine is axial or fluorine is equatorial, interconvert by a ring flip. The equatorial conformation I drew is the same as these other 2 ones that I've drawn. As long as the fluorine remains equatorial, pointing out away from the ring rather than straight up and down, they are the same conformation as each other. There's something I want you to notice about the ring flip. The ring flip converts an axial substituent into an equatorial one. And likewise, the ring flip also converts equatorial substituents into axial ones. In general, there's a preference for substituents other than hydrogens to occupy an equatorial rather than an axial site. I'll delve into why this is the case for methyl cyclohexane. Here I've drawn the two chair conformations of methyl cyclohexane. You can use Me to stand for your methyl CH3 group. In one of these chair conformations, the methyl group is axial, and in the other one, it is equatorial. What's seen is that 95% of the methyl cyclohexane molecules exist typically with the methyl in the equatorial position, and only 5% of the molecules at a given time will have their methyl group at an axial position instead. The reason for this preference for the group to occupy the equatorial position instead of the axial one is known as 1,3 diaxial interactions. Here, in addition to drawing the methyl group axial, I've drawn out all of the hydrogens in their locations around the cyclohexane chair conformation. I'm going to number my carbons from 1 through 6 for reference, with the methyl group coming off of carbon 1. And I'm going to imagine looking at this molecule down the carbon 1, carbon 6, as well as carbon 3, carbon 4 bonds, like a Newman projection. So let's imagine starting out with carbon 1. From the observer's perspective, the methyl group is pointing straight up. The hydrogen on carbon 1 is pointed down and to the left. And carbon 1 is also connected to a carbon 2. From the observer's perspective, carbon 2 is to the lower right of carbon 1. Now let's think about carbon 6, which is directly behind carbon 1. Off of carbon 6, there are two hydrogens. One hydrogen points straight down, and from the observer's perspective, the other hydrogen points up and to the left. Up and to the right, carbon 6 is connected to carbon 5. Now let's imagine our other front carbon, carbon 3, that's connected to carbon 2. Carbon 3 has an axial hydrogen pointed straight up, and carbon 3 also has an equatorial hydrogen pointed down and to the right. Carbon 4 is connected to carbon 5. Carbon 4's bond to carbon 5 points up and to the left, and carbon 4 also has two hydrogens attached. One pointed straight down, the axial hydrogen, and the equatorial hydrogen pointed up and to the right. Now let's think about the positions of our hydrogens at carbons 2 and 5. At carbon 2, there's an axial hydrogen pointed straight down, as well as a hydrogen angled toward the observer. I'll draw this one as a wedge. On carbon 5, there's an axial hydrogen pointed straight up, and there's also a hydrogen pointed down and away from the observer. This one will be drawn as a dashed hydrogen. So, this is our Newman projection of methyl cyclohexane. Notice that my methyl group is axial, pointed up from carbon 1, and there are hydrogens on carbons 3 and 5 that are also axial and pointed up. Having the methyl group close to these other two hydrogens, which are at the position 3 relative to the methyl substituent, is a form of steric strain. We call this a 1,3 diaxial interaction, and this clashing of electron density makes this conformation unstable. The larger your substituent becomes, the more severe these diaxial interactions will be, and the more unfavorable the axial conformation is relative to the one in which your substituent is equatorial. So remember from before, that methyl cyclohexane, for my two chair conformations, I have 5% in which the methyl is axial and 95% in which the methyl is equatorial. If instead you have tert-butyl cyclohexane, 99.99% of the molecules will have the tert-butyl group in the equatorial position, and only 0.01% of molecules will have the tert-butyl group in the axial position. Recall that a tert-butyl group is a branched 4-carbon substituent. Because the tert-butyl group is larger than a methyl, when it's in an axial position, it has more steric clashing with the hydrogens that are pointed up and axial as well. These more severe 1,3 diaxial interactions disfavor this axial conformation. Alright, so in summary, I talked about different ring sizes of cycloalkanes and strain present in 3, 4, and 5-membered rings. In its chair conformation, cyclohexane doesn't have any strain. I talked about how you can convert between two different chair conformations by a ring flip, and the preference for putting substituents at the equatorial site rather than an axial one. That's it for this video. I will see you in class.